So, hi everyone. I'm happy to host Professor Chiaki Kobayashi from the University of Hertfordshire. Never quite know how to pronounce it, sorry. And so Chiaki did her PhD at the University of Tokyo, and she worked all around the world, basically, like from Germany to Australia and to Japan before she settled in the UK. She does a lot of galactic chemical evolution studies. She developed her own galactic chemical evolution code that gave a lot of beautiful results over the years. And today she's going to talk about chemical enrichment and the era of the JWST. So,
thank you. Thanks very much for the introduction. Also, thanks very much for inviting me to this big place, which I wasn't quite aware how many people can come to this talk. I try to keep it general, but I'm very happy to talk a lot more after the talk. I will be around all this afternoon today. So this is my second time to come to Tucson. The first time was the team meeting of the WFMOS. Some of you might remember it was a collaboration between Japanese Subaru and Gemini to have a multi-object spectrograph long time ago. It would be revolutionary, but it didn't happen. And then since then, I didn't have chance to come here, but now we have a similar spectrograph now. And with that, I try to discuss stellar evolution first, and how Milky Way, our Milky Way galaxy can be formed, and then also expand to the story to a larger scale, cosmological evolution. So I heard also there is a student as well in this room, so let's just start with the basics, a few more slides. The universe started at the Big Bang, 13.8 billion years ago. The initial first light we can see is a cosmic microwave background. By analyzing the light, we know that we actually don't know much of stuff. 70% of dark energy, we don't even know the clue. That 26% dark matter, maybe some particles, 5% of atoms, which most of us are working on, from which stars, galaxies, planets, and human beings are formed. And we are now here. We made the satellite look back through the distant universe, meaning we are looking at the universe in the past. My particular interest is even more small fraction, that's only 0.07% of metals, it's called. In astronomy term, this is elements, carbon and heavier elements. So how they are distributed along this history of the universe, that's what I would like to understand. So I'm also working on the simulation of galaxies, and I'm trying to make nice looking galaxies as nice as observed from cosmological initial condition. That's the CDM fluctuation I am in. It's possible to do this now, particularly gravity, if you need a supercomputer, but this can be solved. Hydrodynamics as well, we have to have some method, like smooth hydrodynamic particle method or mesh code. This can be done. Star formation, we actually don't know well how to form stars, so we have to assume something when we would like to form galaxies. The even more subtle part is so-called feedback. What will happen after the star formation? What's the impact? How the next generation of star formation is suppressed by the presence of first generation. So this process is very uncertain. However, once we form stars, what should happen afterwards? This is relatively well known. If formed stars are massive, let's say 10 times more massive than the sun, they explode as quark of supernovae at the end of life. They produce a lot of so-called alpha element, oxygen, magnesium, and so on, as well as a bit of iron. Otherwise, we can't observe at supernovae. And these are massive star cycle, so that it's million years time scale, very fast in terms of galaxy history. Lower stars can do quite a lot of stuff if they are in a good binary system. These are different type of explosion. Type 1 observed as type 1a supernova. These are thermonuclear explosion. And this explosion is very different. Particularly, they produce a lot of iron peak elements, iron and other elements around it. they are binaries and Loma stars, so time scale is about a giga-year, longer than the massive star channel. Single Loma stars don't do so much except during a symplectic giant branch phase, they produce the light element, carbon, nitrogen. Also, some slow neutron capture elements can also be produced here. And this is the time scale, is again giga-year or longer. Massive binaries can make neutron star system. Some of them will merge within the cosmic time. And then that's also the site for the rapid neutron capture elements. Anyway, in a galaxy, different elements come from different sites on a different time scale. If we look at just not only metallicity, but also elemental abundance pattern, we usually take the ratio relative to IR normalized by the solar ratio. All of these quantities evolve as a function of time. So we can use these information as a fossil record to track back what happened in the galaxy. And this approach is very popular, particularly for our Milky Way, thanks to the large amount of data set. And the approach is called the Galactic Archaeology. To compare with observation data, we need to have a model, and then this is a theory, a series of Colloquia. So just one equation I'm going to show today. It's this one. So galactic chemical evolution can be calculated by integrating this one equation. In the interstellar medium, how much mass of each element exists? That's the quantity ratio times the gas fraction. The time the difference of that. So this metal quantity in the ISM increase if there is a new metal production from stars, stellar winds, supernova, or binaries, particularly important channels of type 1a supernova and neutron star mergers. And then if there is a star formation happen, I enjoy the desert park very much. It's a star formation, that's a part of star here. Anyway, these metals move from gas phase to stars. So there is a negative component here. And we are talking about galaxies. So if there is inflow of material or outflow from galaxy to outside, there will be also a change depending on these terms. The first three terms, I call it a nuclear astrophysics term, and I've been working with my close collaborator and friends for a long time. The most important factor is nuclear synthesis yield, how much element comes from each star or each supernova. For galaxy point of view, we also have to know how many massive stars exist in the system. In other words, initial mass function is also an important factor here. And then type 1 supernova neutron star merger come from binaries. We have to know the binary physics, which is not very well understood. And also what's the progeny does are, these are also included in this modeling. And the most importantly, there's nuclear reaction rate. Nuclear physicists try to measure how much elements should be produced in each nuclear reaction channel. So that's also the background information. The last three terms, I call this is a galaxy evolution term. So here there are various ways. One extreme, most simple way is, let's assume star formation, inflow, and outflow with a very simple analytic formula and calculate evolution of chemical abundance. This is very simple, but it's actually a very useful way. And these models are called one-zone chemical evolution model, but they're very classic. I can do this galaxy entire history with 2 minutes on the laptop. The most sophisticated end is this inflow, outflow, and star formation should happen based on the physics. So if we are able to resolve ISM physics very accurately, there should be no parameter associated. We are not there yet, but this is a possible direction. So all of these galactic terms should be given by hydrodynamics. And to do that, we need to have a big supercomputer. And I'm using the UK facility called Iraq. This is now I'm talking about using million CPU time, running it for more than a year to simulate one Milky Way type galaxy. That's the scale I'm talking about. And yet we are not able to resolve star by star I am going to talk about star particle later on to describe galaxy history. So a bit more background. So the star evolve, and then the life of stars depend on the initial mass of stars. These numbers are the case of single stars. I know some of them are working on binaries. If binaries, this initial mass to final mass ratio will be shifted. So you can do the conversion in your head. Let's stick to the simple story. If stars are very small, they don't even fuse hydrogen. The normal star can have hydrogen, they can shine thanks to the nuclear energy converting hydrogen into helium. And then there is a helium flash, carbon to oxygen core will be formed. That's the stage for our sun. Our sun will end up in this area. If stars are more massive than the 8 solar mass, they can also fuse carbon at the center or near center that will form oxygen and magnesium core. Quite a few stars actually finish there, and some of them may explode as electron-capture supernova. But if you hear many times core collapse supernova, that's the next stage. Stars greater than 10 solar mass will have iron core. And this is a classic picture of core collapse supernova. This is an iron core collapse, and the product will be neutron star or black hole. Supernova explosions we see in the universe, but it's actually not easy to simulate. Until several years ago, we don't see any successful simulation that can explode stars in a computer. Now we can see various successful cases. The left side was, it's finished already. Anyway, the lower side, you saw this quite inhomogeneous structure when the stars are trying to explode, and then thanks to this neutrino-driven inhomogeneous expansion, we can see successful explosion up to 20 solar mass or so. Sorry, I'm losing the, okay, that's good. So up to 20 solar mass or so, we can see both in the real universe, like 1987A is a core collapse supernova happened in the Large Magellan Cloud in 1987. So supernova naming is pretty easy to remember what happened. Up to there, we can see this neutrino-driven mechanism explode. Above 25 or 30 solar mass or so, we don't see any successful explosion because gravitational potential is just too deep at the center, and then stars don't usually explode. However, in the observation, namely observed supernova light curve and spectra, it's possible to estimate how much energy is produced, also how much iron is produced from each supernova. And when we do this, we actually have some points here in red. So these are more energetic and more massive stars. So we don't have this good model theoretical point of view yet, but we see them quite a long time. And a long time ago, the Japanese group have this naming of hypernova. These are, in terms of type, they were type 1 BC broad line 1. But the famous example is 98 PW. This is one of the first example associated with long gamma ray burst. So I'm saying I'm running chemical evolution model, including this hypernova, and found to be this is very important. I have to have quite a lot of them at low metallicity, in particular, half of more than 20 solar mass should go into this channel. Otherwise, I cannot reproduce chemical abundance observation in the Milky Way. Final product will be neutron star or black hole. So we have now independent observational constraint from gravitational wave missions. Lots of black holes. How to form this massive black hole is an interesting question. I'm focusing more around here. Neutron star mergers, also neutron star black hole mergers. These are the site of rapid neutron capture elements. So I've already touched the type 1A supernova. 1A is very famous thanks to the Nobel Prize went to type 1A supernova for measuring accelerating expansion of the universe. So you hear the 1A many times, but actually, what are they? What's the progenitor of type I supernova? It's not well established yet. We actually don't know very well. So two scenarios are here. One is classical one. There is a one white dwarf made of carbon and oxygen. There is a normal star in a companion. Mass accretion takes place, and some of the matter will be lost. And with some very good nano range of accretion rate, white dwarf can increase the mass to reach Chandrasekhar mass and don't explode. This scenario is good because you can expect homogeneous luminosity for type 1A supernova, and that's obviously useful as a cosmic clock. However, there are a number of problems is pointed out for this channel, and then now people are thinking different channels, such as merging of two white dwarf, and in this case, many cases, explosion will be much less than Chandrasekhar mass. The chemical point of view, there is a big difference. So the Chandrasekhar explosion is more high temperature, high density explosion is happening at the center. And this is very useful to form particular element, manganese. But theoretical calculation says this sub-Chandrasekhar mass can make a bit of iron, but not so much manganese. So this is a problem of this second scenario. And still, we don't have the best models yet. So now I am going to use the observation of Milky Way, just to remind you, in the Milky Way, thanks to ESA Gaia, we have a detailed kinematics of many stars, many of the cases, also the good estimate of ages of stars. And then thanks to the follow-up observation, we have elemental abundance from lithium to europium of millions of stars. And then some of the interesting elements, particularly my favorite gold or heaviest element uranium, can also be measured, but this is only handful of stars because of the wavelengths of the atomic lines we can use, and that's a UV range. So in this Milky Way science, metallicity is often equivalent to iron abundance here, and square bracket meaning normalized by the solar ratio. So 0 is the solar abundance. You can see in the following figures. This indicator will be different when I talk about extragalactic observation later on. So this is the most famous diagram of galactic chemical evolution. It's called alpha to iron ephemerobiology diagram. Y-axis here is metallicity, iron abundance, and then on the y-axis we take two elemental abundance ratio. One of the alpha element, let's take oxygen here, relative to iron. So we know these points are observed, a very accurate observation of individual stars near the solar neighborhood. And then we know this, the points are almost flat, and it shows a decreasing trend. That's the relation I am going to talk about. So time roughly go from left to right. As you can imagine, metallicity increases as a function of time overall. The beginning of the universe, the first star, is made of zero metal gas. So it's in these coordinates, minus infinity. So the story starts from outside of this coordinate. And then they are also called population tree stars. We don't know what are they. We don't know mass or the fate of these stars. But we can study what were they by using extremely metal poor star. That's called EMP stars. They have the iron abundance less than -3. Detailed elemental abundance are obtained, and from the analysis, people have been working on what was the first stars in the Milky Way system. Then these extremely metal poor stars evolve and explode as normal supernova, type 2 supernova, and also hypernovae I highlighted earlier, and then enrich still low metal universe, and they are called population 2 star, also halo star, the stars with a halo of it. And they are the value, almost flat alpha to iron ratio with a positive value. These are stage still early phase, mostly enriched by type 2 supernova or hypernova. Both produce mostly oxygen and small amount of iron. Around Fe over H, the story is changes. Type 1a supernova becomes dominant. 1a produced only iron. So in this coordinate, this alpha 2 ion sharply decrease to the 0, by definition, that's the solar ratio. And about 5 gigayears ago, the model line goes through here. And we are, since the sun is formed here, and we are now only this tiny area we are living. And the stars are observed. These are population 1 star on the disk plane. And then you see some stars around there, also down there. In the extragalactic community, this alpha to ion ratio often used as an age indicator. Like high alpha is recognized as old population or early type galaxies, while low alpha is the other way around. But this is not a linear trend. It's a plateau and decreasing trend. So that's should happen everywhere in the universe. So chemical evolution model is I'm using here is a very simple analytic calculation. It has to be, there is a free parameter for star formation inflow and the outflow. These are calibrated by using other observation as well as many elemental abundance I'm showing here just as a slide. Zinc to iron ratio is found to be very important because this is the unique signature for energetic supernova, hypernova. I really needed to explain this observed zinc abundance here. My model can also do the neutron-capture element as well. And europium is another interesting element. That's one of the popular R process element, rapid neutron-capture element. And that's quite high from the beginning. And that's indicating our process should happen in a massive stars without going through binaries. The same model, I showed this summary slide showing in a periodic table style, coloring the origin of each element with a different from the different side. The Big Bang nucleosynthesis is colored in black, so it's the Big Bang nucleosynthesis produced only light elements only. So hydrogen, helium, lithium are blacked out already. Beryllium, boron are not included in my model, so ignore this. And then metals, carbon onwards are produced by stars. So different from similar periodic table, there's another periodic table over there. We are forced to replace this one. So this one has more information. In each little box, there is a time evolution. So very left side is time 0, and then the rightmost is now, and the vertical, this dotted line is a time the sun is formed. So horizontal dotted line indicate observed solar abundance of each element. So my goal is adding all these production site and go through this crossing point of dotted line. So that's my goal. Yes, please.
So when I hear people talk about production of the R process, these people give that all to neutron star mergers instead of core collapse, whereas your diagram here says just the opposite. What's the resolution here?
Yeah, so that's the exact point. I am going to neutron star mergers are included, but it's found to be very small from the theory. Let me go one by one. As you pointed out, the most of stars are coming from blue area, which is massive stars. And the reason is including not only normal supernova, but also electron capture supernova. I mentioned relatively normal size 8 to 10 solar mass. And then rare energetic explosion, probably driven by magnetic field and rotation, magneto-rotation supernova, and hypernova as well. So that's why you see even the heaviest element, uranium, is highlighted with this blue area. Binaries 1A contributes around the pink element already mentioned. The neutron star merger is also included in similarly following the prediction of how many neutron-star-neutron system exist, how many and when they explode. These are provided from binary population synthesis, theoretical calculation. Rates are consistent with LIGO detection. And yet, as you see, the magenta line is very small. One notice this y-axis here is not logarithmic. This is now linear scale. So you see very small, only very tiny contribution from neutron-star matter. And this was a big surprise, but this is what we get in our chemical evolution model. Back then, when we published in 2020, this diagram was a bit shocking to the people working on gravitational waves and binary the modeling, and I was told no, neutron star merger should be the main producer of our process. But we haven't seen clear neutron star merger since 2017. There is one in 19. Last week, there is another candidate was reported, but at max only 3 events we saw neutron star merger. Back then, I was feeling maybe I was wrong, but now maybe I was not wrong. In nature, neutron star merger is actually rare, and we need to have massive stars, not single massive star even, to produce our process elements. But this is still ongoing work. I'm also writing another forum paper, including binary people, to address, can neutron star merger only explain the Earth process observation in the Milky Way? We tried various different binary population synthesis theoretical calculation. We also updated applied higher rates, including higher nucleosynthesis production per event. And then in a most optimistic case, this blue line, I can even get 0-0 ratio neutron star merger only. So neutron star contribution will be slightly higher than I presented in a periodic table, but still this low metallicity area, the neutron star merger only cannot reproduce this trend, and then we should have some massive star exploding to producing our process element. But magnetic rotational supernova is one possibility. The same story, but in the previous model was one zone calculation, and this can depend on the assumption of star formation, inflow and outflow. Let's run the hydrodynamical simulation and remove this uncertainty of star formation history. And in this case, my former PhD students switch on and off each side. If it's AGB only, of course, europium is not enough produced. Electron capture supernova also do not help. Neutron star merger only, in this case, it may be possible to reach 0-0 line, but the scatter in these small points are the simulated star particles in the Milky Way simulation. The scatter is much larger than observed. With including core collapse supernova origin, the scatter can be reduced inconsistent with observation. So not only the normalization, but also scatter is a problem for neutron star merger on this scenario. Where these most massive elements, the europium may be okay, normal supernova can do, but heaviest element like uranium, gold and uranium, where they can come from. Dynamical ejector of neutron star merger, this is already included, and I showed this is not enough. We need something else. Magnetic rotation supernova is also included. I used slightly old yield. That was good. I can get uranium as observed, but the more recent calculation may be indicating this is not a very good side either. So in this case, that neutron-rich matter is ejected along this jet. Another possibility is collapser. So now the matter mostly collapses into black hole and they become gamma ray, long gamma ray burst. But this disk, maybe small amount of disk can be ejected. And that could also be a very neutron-rich. And we also write a paper with Aldana, with other channels. Magneta is also discussed recently. This is not well understood. But something neutron star, something else with a short, very short time scale, like massive star oriented event is really needed for the production of heaviest element. So another very unique star I'm going to highlight here is an extremely metal poor star. Fe over H is minus 3.5, very low, yet very unusually, we get the clear detection of thorium and uranium. Beautiful R process pattern also here, and unexpectedly clear signature of zinc and nitrogen. So this is supporting rotating massive star explode as jet-like explosion, producing R process element. So this paper indicates the R process site can be massive star, but also indicating importance of stellar rotation in the early universe. I'm coming back to this point in relation to external galaxies, high redshift galaxies. So now I am going to show some hydrodynamical simulation of galaxies. When I do this, I find solving hydrodynamics background and dark matter and find a cooling gas and form a new star particle. Because of the numerical resolution, this is not a single star, but an association of stars. I still have to assume initial mass function and the time scale of star formation as well. Then I form the evolution, I follow the evolution of star particle, initial stage stellar wind, heat up the interstellar medium a bit, but most exciting thing happens at the supernova. A lot of thermal energy is produced, as well as heavy element production. The same star particle evolve further. The later on, type 1a supernova also produce energy and ion. And final stage is almost collisionless particle. Black hole, neutron star, white dwarf, they don't do anything, just as a dynamical force and then moving around inside the Milky Way. So Milky Way, this was enough. But later, I'm going to show massive galaxies. And in massive galaxies, we have supermassive black hole. So in our calculation, we assume black hole seed come from the first stars. There is a direct collapse of gas, which form about 1,000 solar mass of black hole. And then we follow the growth of this black hole seed by merging with the other black hole, also accretion onto the black hole. Then finally it becomes supermassive black hole, started distributing thermal energy to the surrounding matter. So I said thermal energy, so that's our fiduciary model, but how to distribute this energy is uncertain. I've already touched feedback, and then there are various ways to do this, like in a kinetic form, pushing out the gas from the center of a galaxy, or some random function associated stochastic weight, or mechanical feedback. So this is highly debated in galaxy simulation community. This is an example of a Milky Way type simulation from cosmological initial conditions. The large scale view, you see the satellite galaxies are formed, and the central component galactic bulge is formed already beyond redshift 8. So central part formed very quickly, while disk grow much longer time after the accretion of gas onto the plane. And you see now Milky Way, a spiral structure on the side, and then inclination will be corrected later on. So this is lambda CDM initial condition. So we see this continuous accretion of small satellite galaxies. Many are disrupted, became halo star now. Disk is now stabilized, and then there is occasionally emerging debris comes in. We see merging event of Gaia and Enceladus is one of the famous example happened in the Milky Way. But not so many aggressive events. There is no major merger in the case of Milky Way. If there is a major merger, this disk structure will be destroyed. So this simulation includes, I was showing the stellar light distribution, but this simulation includes chemical evolution as well. So I can show you the metallicity map of the same galaxy face on and the edge on view. The red color is more metal rich. Roughly speaking, the center of the galaxy is more metal rich. There is a radial metallicity gradient. Also, there is a vertical gradient too. And this simulation looks pretty similar as real data. Gaia also have metallicity map. That also quantitatively it's pretty similar. You see this blue component in the center, but this is an artifact from Gaia data analysis. In real Milky Way, the central part is just old and metal rich. I was talking alpha to ion ratio earlier, and in this case, figure looks very different. So on the edge of view, we expect alpha to ion is roughly 0 as for the solar abundance. While there is a strong vertical gradient. Higher altitude, the halo star have high alpha. They have star formation in the early universe and stopped. No typhoon A enrichment in the galactic halo. That's causing this high alpha. This simulation has a bar, and then along the bar, the gas accretes and then keep forming stars. So there is a blue bar in this particular lab. That was interesting point. And I can show you the same Gaia data. Also, Gaia shows this strong vertical gradient of alpha to ion ratio. And then the same alpha to ion diagram I showed earlier. So earlier was a simple one zone calculation. You saw only line, but now it's a hydro simulation. At a given metallicity, there is a scatter. That's the important thing. The real observational data also have a distribution. So we can compare this kind of simulation to the large number of stellar observation directly. Same feature is still seen. There is a plateau caused by quark-group supernova with a positive value. And at the same place, if you by -1, there is a decreasing trend caused by delayed enrichment of type 1 supernova. One important difference from previous figure to this figure is the distribution. So you see more stars around here, and then there is a kind of gap and another down there. So this bimodality is one of the big topics in the Milky Way science, thanks to the large amount of data. This bimodality appears slightly different depending on the radius and latitude of the Milky Way simulation. We are here. The solar neighborhood is on the plane. Observational data show very similar thing. Good thing is simulation also have a kinematics. We know exactly what are they. So I can color depending on the kinematics. Now V over sigma, blue meaning more rotational supported, and this low alpha component is indeed rotational supported system in the plane. While in the same solar neighborhood, there is also thick disk component, random motion stars as well. So we think the origin of this bimodality is this difference in the kinematics. The next question is there similar alpha to ion bimodality exist in other galaxies? The only place we can do the very accurate analysis is this one, M31. And I know people are working on here. We're using DESI. Is looked at quite large area of around M31. Before the DESI time, it was not easy to estimate elemental abundance of normal stars. So we looked at planetary nebulae instead. In the case of planetary nebulae, the available elements are different. Iron is not available. Oxygen is available, and we used argon instead of iron. In any case, we see two parallel sequence also in Andromeda galaxy. And in this paper, we said bimodality is probably universal. Other galaxies, we can use IFU data. If it's edge-on, we can see similar bimodality on some of the edge-on galaxies. I think it's universal, but that's JWST, more JWST observation is going to do other location observation with JWST. In that case, we can measure elemental abundance of individual stars, red giant stars. So the Milky Way simulation also have various satellites. I don't have time to go into the detail, but my current postdoc is trying to analyze elemental abundance of satellite galaxies in the same simulation run. And then we get this mass metallicity relation as well. If some of you are working on dwarf galaxies, I'm happy to talk more later. And I'm gonna jump on to high redshift galaxy one. So I think I have another 10 minutes or so, I think, yeah. So now each point will be galaxies. It's now a different story. So it's possible to get metallicity and elemental abundance of 1,000 galaxies. Elemental abundance are available only for the limited set, but it's a good set. Carbon, nitrogen, oxygen, neon, sulfur, and argon is a very important element as it can behave like an ion. Coming back to this later. Ion is also estimated for some cases, but this is very challenging. I think it's better to use argon instead of ion. And some of star formation history can be constrained from SED, or some kinematics also available with ion field. But observational data are more limited compared to the Milky Way case. And then metallicity is usually oxygen abundance without a square bracket. So you see like 8 or quite large value here. And for your reference, solar abundance I'm using is 8.76. Then now the same code, but applying to a large volume of cosmological box. And now I'm showing how elemental abundance changes as a function of time in a movie. And this is a large volume simulation, but focusing the central most massive galaxies now. So this is a center, it's the most massive galaxies in this run is produced. I'm gonna run it again. So that already you see that the metallicity distribution is very inhomogeneous. Along the filament, even before the massive galaxy appeared, some area, the white is supersolar metallicity. And then it's very quickly. This was supernova-driven galactic outflow distribute heavy elements around the galaxy already. Some of the elements accrete toward the massive galaxies now. And the very final moment, supermassive black hole was puffing up the elements from galaxy center to intergalactic medium. That was happening in this simulation. So how much element is produced from each galaxy? In the simulation box, we can do this. We can just measure how much element is ejected from each mass of galaxy. So now x-axis is stellar mass of individual galaxies in the cosmological volume. And then we find most of galaxies are along this zero, meaning net in and out metal flow is roughly zero. Slightly negative, so that most of galaxies are slightly gaining metal, but not very much. But we see also this trend, more low mass galaxies have lost metals by supernova-driven winds. And then that's in the most massive low mass case, like 60%, more than half of metals produced inside the galaxy are not there. It's ejected and then lost. And massive N, on the other hand, small number of galaxies have lost up to 20% of metals by agent-driven winds. So supernova winds are including all mass of these points, but it just potential is too deep to remove the metals from the galaxy. And the massive N, only AGN can actually remove metals as expected from various observational signature. The color showing the deviation from star formation main sequence. Long story short, the red one is more early type, quenched galaxies. And indeed, these are just removing metals and also stopping star formation. While blue area is star formation is still ongoing, self-regulated, in and out, balanced. So that's happening for the majority of galaxies, particularly low mass end. I touched the uncertainty of feedback, and my current speech issue then changes the supernova feedback. It's a bit cut off, but the first one is thermal feedback, and this is stochastic one, and kinetic feedback and mechanical feedback, and how metallicity distribution is not different so far, but it is different in this case. The kinetic feedback is so aggressive, it's redistribute heavy element distribution dramatically. This is a temperature distribution as well here showing. So this feedback description is very important when we look at the scaling relation of galaxy. So here, the different color shows how these feedback methods affect mass metallicity rate of galaxies. By using multi-object spectral observation as well as JWST galaxies, it should be possible to constrain which feedback description is better. So what I want to highlight is elemental abundance. Elemental abundance is better because this is relatively insensitive to the feedback description. We just have to get the element production correctly from the stars depending on the mass of stars. At higher redshift or even external galaxies, alpha to ion ratio, the diagram I was showing, is not useful because of ion. Ion is very difficult to measure. So instead, the community was using nitrogen to oxygen ratio already long time. So the local trend is known, that's the gray bar. So x-axis the oxygen abundance, and nitrogen to oxygen ratio stays flat at low metallicity and shows increasing trend. So this is a reverse trend compared to alpha to ion I was showing earlier. Interpretation is a bit different. So increasing trend is caused by metallicity dependence of nitrogen. So nitrogen is produced by CNO cycle, hydrogen burning, but CNO cycle. CNO cycle, to start with, you have to have carbon. So that's why have to have metals to start with. Higher metallicity stars, nitrogen is will be. Plus AGB also enhance nitrogen as well. Then Loma side is in a hydro simulation case, the small amount of AGB happens cause inhomogeneous enrichment. That was enough to explain in our case. Or some people said rotating massive star should be important to explain this plateau of nitrogen to oxygen ratio. This was debated. The color points are simulated galaxies. Each point is galaxies. And back then in this pre-JWST time, we were able to reproduce this local trend nicely. Galaxies really evolving along this relation as a different redshift color here. We were happy until JWST. That's one of the famous one, GN11. The value was even outside of box. So GN11 is a galaxy just only after 430 million years after the Big Bang. Redshift 10.6. It is a galaxy. It's compact, but that's the one. And then the most striking part is this the beautiful spectra shows this particular area. That's very strong nitrogen dye, indicating nitrogen to oxygen ratio is very high. Now the solar abundance is minus 0.33. So it's compared to this, it's a lot higher than the solar ratio. This was a big surprise. And many papers are now on the published and also on the archive. Some people are pointing out the similarity of the stars in the nearby globular clusters, or maybe indicating exotic source like supermassive stars. The first question we think is a nitrogen enhanced galaxy. Is it only high redshift thing, or can we see similar thing also local universe? And my postdoc Suraj Bhattacharya looked into DEGI published data and then measured nitrogen to oxygen ratio. So all these DEGI points are the measurable galaxies. As we started from 14 million galaxies, but only 1,000 galaxies we can get a good measurement of nitrogen to oxygen. And then most of them located down there. It's the same plateau and increasing trend, the same local trend. But we found small number of galaxies up there. These filled black points are also DEGI galaxies. And then it's only 2%, small fraction, but there are such local nitrogen emitter, meaning nitrogen to oxygen ratio is high. Here, we are also comparing to high redshift galaxy sample. That this triangle was GNZ11 already highlighted. These are the UV and nitrogen lines are used, while some slightly lower galaxy sample have optical nitrogen measurement. Similarly, nitrogen enhanced, but maybe a bit different. So this is also debated in the extragalactic community. What's the exact value of nitrogen oxygen ratio? The shaded areas are my collection of, this is one zone calculation, but changing star formation time scale within the reasonable range. And the standard model without strong outflow is going this direction, explaining local trend very nicely. Or if we include outflow, oxygen is selectively lost. We don't tune by hand, but just because of the time scale difference of the production, oxygen tends to be removed from galaxy. And hence, nitrogen oxygen ratio will be higher. That's the yellow area. Most of galaxies can be explained with this outflow scenario. Or sometimes, like in M31 case, sometimes there is a dilution of gas. And if inflow happens, the line goes to the left side, just hydrogen is enhanced on this y-axis. So in this case, this loop trend can also explain this very high value, including GNZ11 as well. So we think the GNZ11 is a similar category. That's my GNZ11 model of one zone calculation, but proper chemical evolution models here. And in this case, we have new nitrogen production from rotating massive star. Some of them go through Wolf-Rayet phase. We don't have to change IMF. We just have to have Wolf-Rayet, but intermittent star formation. The story is the following. This is the redshift 10 galaxy, but star formation have started redshift 16 or so. Nitrogen was very high beginning. This is the only first generation Wolf-Rayet. But soon after, quark-group supernova happens, and nitrogen to oxygen ratio is already as low as the solar ratio. Assumption was that there is a secondary gas inflow that brings the line to the left. And the secondary Wolf-Rayet stars producing nitrogen more before secondary quark-group supernova happens. So this narrow range of this really narrow range of the time, nitrogen to oxygen ratio it can stay very high as observed. And this story works pretty well. I don't need any extras, any supermassive star or anything exotic. Just assuming bursty star formation, that's quite possible. The galaxies are still small, and then many things are going in a high redshift. In that case, we can get small number, possibly a couple % of galaxy go into this phase. How many exactly? We have to have a large-scale cosmological simulation. That's my current student is working on. So we hope to see how many nitrogen emitters exist along cosmic time. Another element hinting the same thing was oxygen to argon. So 30% of argon actually come from a type 1a supernova. That was already shown in a periodic table. I forgot to highlight, but it was the case. And using this nuclear physics knowledge, we can plot oxygen to argon as a proxy of alpha to ion ratio. And this value, of course, decreases as a function of time because 1A produces more argon at higher metallicity. Many high redshift galaxies, these stars, along the same Milky Way model. So it's a more self-regulated one. Slightly massive ones are at higher alpha to ions. That's also expected. But some galaxies are even down there, more argon. One way to explain this is a bursty star formation, the same, similar to GNZ11, but slightly different way. And then this loop model can explain this sparsity star formation, even for this oxygen to argon. This one galaxy may be interesting now. This is the most high redshift galaxy we were able to measure argon abundance because of the wavelength coverage. This is redshift 7. And it shows very low oxygen to argon. This could be still outflow driven model, or could also be pointing to the very fast stars. So I'm not sure I have time to do this, but anyway, very massive stars beyond 140 solar mass or so will explode as pair instability supernova that have a very unique signature. One signature is high silicon sulfur to oxygen ratio. Also, argon abundance is expected to high. This pair supernova is a very strong signature. In the Milky Way, we don't see any signature, and probably in Milky Way, periphery supernova did not happen at all. But in other galaxies, maybe. So that by looking at elemental abundance ratio, by looking at carbon, nitrogen, oxygen, as well as argon, we should be able to see the signature of population tree star enrichment in the early universe. This is some example we try to constrain IMF by using CNO abundance at once. And that's all I have prepared today. I started with origin of elements. We have good enough understanding to use this nuclear astrophysics knowledge to Milky Way and external galaxies. At the same time, there are also unsolved problems. So nuclear physics is also important. We have still more things to do. Milky Way, I highlighted alpha to ion bimodality, and then in extragalactic thing. Now it's more elements are available, and then we might be able to see some population tree star signature. Thanks very much for listening.
So let's give time for some questions. Yes.
Hi, thanks for the great talk. So you showed that with hydrodynamical simulations, you get a scatter in those chemical evolution plots. So what is it that primarily drives that scatter? Is it mergers and interactions or more secular processes, star formation, feedback? What is it?
Mix of them, but the important thing is the scatter in age metallicity relation. So at given age, the gas is inhomogeneous, some areas are metal enhanced. Another effect is, I didn't mention, but stellar migration. Even stars formed in the same area, but they don't stay at the same place. Some areas are enriched in a different place and come to the solar neighborhood now. So roughly speaking, 1/3 of scatter come from intrinsic variation, meaning ISM is inhomogeneous. Another 1/3 come from this merger origin, some are coming from the satellite galaxies. And then another 1/3 is each supernova produce different alpha to ion ratio. So this stellar variation is also responsible for the scatter.
More question? Yes.
Great talk, very stimulating. I want to go back to the R process things. I have a few questions to put together. One is that there are two elements to the competition between neutron star mergers and core collapse. And the way I always heard it is, well, you need the neutron stars because core collapse, won't produce enough of the stuff. So if you take away the neutron stars, you then have to have a way to boost up the core collapse beyond what people think. And then there's two things that go with this is one, of course, neutron stars are made by core collapse. So those two are always going to be coupled together, they cannot be arbitrarily separated. And I guess the last part of the question is, I wasn't quite sure how much you were putting on the observed LIGO rates. of neutron star mergers, I might postulate that, this is say nonlinear with star formation rate or the conditions that neutron star mergers might have been, a stronger function in the past rather than what LIGO is able to see right now.
Yeah, so just remind you that the present LIGO rate and binary population species prediction I'm using are consistent. But as you pointed out, in the past, we don't know. Maybe future mission, Lisa or something else will give us some hint, but we don't know yet. However, elemental abundance, I was comparing earlier. Maybe let's go back to, oops, not this one. These are the stars we observe now, but low metal stars are formed in the past. So this is like a time machine. We can see how many neutron star mergers should happen at low metallicity time. That's many giga-year ago. This is a logarithmic plot. And then here, for example, if neutron star merger only, that's the dashed line, is much lower than any of these observed point. So I'm boosting by adding supernova contribution from this dotted line to this solid line. So that's the like Milky Way. Low mass star observation is like a time machine.
We have time for one more question. Ask away.
My question was on when you show the cosmological simulation and show the metallicity kind of starting to raise along the filaments. Is it because you're forming stars before you form the galaxies? Like, why is the metallicity going up before you form the galaxies?
Yeah, that's right. Before, well, stars formed first, yeah, and then, well, gas collapse into the dark halo forms first. The gas collapse, and then stars form. And more stars formed, and then also suppression is ongoing, self-regulation growing, and galaxy looking object appears. And then the movie I was showing was a gas phase oxygen abundance. And if I show the stellar continuum of galaxies, it looks a bit different. You don't see this clear filament. It's more like dots appears when the galaxy is formed.
Okay, thank you again for a great talk. And Chiaki is still here today, and I think not tomorrow.
Not so sorry. We have to drive out, but
Yes,
very enjoyable.
today, and we still have one more spot left for dinner because of a last minute cancellation. So if someone wants to join dinner, then please let me know right above after the talk.
Where, when?